this theorem, the second derivative test for local extreme values, it was the main point of our previous video here. And it feels like I've been stalling in this section here. I haven't done any examples. So let's rectify that. Let's actually carry out a nice, well-worked example here. So let's find and classify critical points of f of x comma y is x squared plus y squared, all of that times e to the negative x. So how do we go about doing this? So we're going to break this down into a couple steps here. So the first part is going to be find critical points. How do we do that? Remember, critical points, that's when the partial derivatives are both going to equal 0 here. Everything will exist. We don't have to worry about the does not exist case. So we need to compute fx, set that equal to 0, compute fy, set that equal to 0. So if we take the partial derivatives, let's go ahead and do that. The x partial derivative here is going to be, okay, so we have to use the product rule because there's x in both this term and this factor and this factor. I take the derivative of e to the minus x. Yeah, so I'm going to have x squared plus y squared times the derivative e to the minus x, which is minus e to the minus x. Now I'm going to leave the e to the negative x alone. Take the derivative. When I say the derivative, I need to be clear. I should have been being clear. We're taking the derivative with respect to x. X partial derivative. The partial derivative of x squared plus y squared with respect to x is going to be 2x e to the negative x. And then the y partial derivative. E to the negative x is a constant with respect to y. So this is just going to be e to the negative x times the partial derivative of x squared plus y squared with respect to y, which is 2y e to the x. Okay, so we found the partial derivatives. Let's set them equal to 0. E to the negative x, that's never going to equal 0. And so the only way that we get something equal to 0 to y is equal to 0, which shows us that we must have y equal to 0. For this case up here, then, we can factor out both of these terms have an e to the negative x in them. And so we'd end up with 2x minus x squared minus y squared is equal to 0. And so we know that y must equal 0, so that's equal to 0. E to the negative x can never equal 0. So we can multiply both sides by e to the positive x to get rid of that. And so we are left with here 2x minus x squared is equal to 0, or x times 2 minus x is equal to 0. So x is equal to 0, x is equal to 2. So y is equal to 0, and x equal to 0, x equal to 2. We have two critical points. X is 0, y is 0, x is 2, y is 0. So this is step 1, is finding our critical points. Step 2, let's go on and compute the second order partial derivative. So we need fxx, fyy, fxy. Okay, so if we take start off with fy here. We take the derivative 2y e to the negative x with respect to y. I think we will just get 2 e to the negative x. If we take for fxy, this is of course also equal to fyx. It doesn't matter, if everything's nice here and everything here is nice, it doesn't matter which order we do the partial derivatives in. So let's take the derivative of fy with respect to x here, And we would get, looks like negative 2y e to the negative x. And then finally, we would have to, so this expression right here, e to the negative x times 2x minus x squared minus y squared, that is f of, yeah, so let me say it's partial derivative with respect to x of e to the negative x times 2x minus x squared minus y squared. And if you crunch this out, I'm just going to write down the final answer. It's 2 minus 4x plus x squared plus y squared times e to the negative x. If you're feeling uncomfortable with partial derivatives, it'd be good for you to practice with that. But yeah, I guess I should have written down step 2 is compute second order partials. And so then finally, step 3. Step 3 is to put everything together, is apply the test. Second, apply the second derivative test. And so something that many people like to do here, is to make some kind of chart to help them do bookkeeping here. So by this chart, what you do is that, so we're going to put down columns here for the critical point, the 3 second derivatives evaluated at those critical points, the discriminant, and then we conclude with our answer here, the type. So our critical points were 0, 0, and 2, 0. So let me put that into our chart, 0, 0, and 2, 0. And so now we need to evaluate, we need to evaluate each one of these 3 partial derivatives, second order partial derivatives at 0, 0. When we plug in 0, 0 into this, all of those terms are 0. E to the negative 0 is 1. 2 times 1 is 2. When we plug in 0, 0, x is 0 into 2 to e to the negative x, 2e to the negative 0 is 2. And when we plug in 0, 0 into f of x, y, negative 2 times 0, e to the negative 0, that's going to be 0. Okay, how about for 2, 0 here? When we plug in 2 in for x and 0 in for y, so that would give us here, so this would be 0, we'd have 2 minus 4 times 2 is 8, 2 minus 8 is negative 6, plus 4 is negative 2, e to the negative 2. We plug in, again, that into fyy, we get 2e to the negative 2. And then for when we plug into fxy, negative 2 times 0, e to the negative 2 is 0. Okay, so at this point, we've done the second order partial derivatives. Now we need the discriminant. So we do this times this minus this squared. This times this minus this squared. 2 times 2 minus 0 squared is 4. And negative 2e to the minus 2 times 2e to the minus 2 minus 0 squared is minus 4 e to the minus 4. And so the last thing we have to do is go back to this slide here to read off our information. So this first one, D is 4. 4 is positive. So we're in, it's a local max or a local min. And we take a look, this is, fxx is positive, so we're in the local min bucket. Meanwhile, for 2, 0, d is negative 4 e to the negative 4. That's something negative. So if d is negative, there's nothing else to do here. We know that this is a saddle point. Ooh, not saddle point. Okay, so this is a fairly typical example here. So just to recap, this is the longest video, let's just recap what happened here. To find and classify critical points, we found the critical points by taking the respective partial derivatives, setting them equal to 0. We found 2 critical points. We calculate out the second order partial derivatives, and then using this chart here, we were able to apply the second derivative test. We had to look at the information and compare it with this theorem here to do this classification. So this is the general outline for how do you solve this kind of problem from section 14.7.